Hey gang, so we are into testing our data. So specific types of data require specific statistical tests. We are going to talk about 4 in particular. The table below shows a summary of 4 general types of data and the tests we use them for. Some of these you already know. You already know chi-squared from your biology. So now you may not remember how to do it. And when Mr. Hayes came in the other day, he was like, "Are y'all going to do chi-squared?" And I said, "Yes." When you do chi-squared, you're looking at nominal data. Remember, nominal are things like male, female, left-handed, right-handed, ambidextrous, cars, trucks, motorcycles, vans, the color of your eyes, nominal data. Then you have ordinal data, first, second, third, small, medium, large, degrees, ambivalent, agree, or I said degrees, oh my gosh, disagree, ambivalent, and agree. For these, when you want to rank something like first, second, third, fourth, and so on, we use something called Spearman's rank correlation. It's one of my favorite types of statistics to use. I absolutely love it. Then you have intervals. What if you have like years, temperature, things like that? You're going to use Pearson's. Pearson's you already know as a linear regression. You already know how to do that. Then you have ratios, measurements of lengths, distances, area, time, speed, acceleration, things like that. Again, that's Pearson's. It's a bivariate, meaning we have an X and a Y, bivariate data analysis, okay? We are going to focus on these right here. Chi-squared is a unit on its own, just because it's something a little different. Hopefully you remember it from science, but if not, no worries. So we're going to focus on these down here. So turn your page and let's look at what we have. So you already know this, so I'm going to go a little bit faster, I think. In real life, it is sometimes hard to pinpoint causation. For example, take this statement. If you commit a felony, you do something wrong, you will go to jail. Maybe you might go to jail. The jury might find you innocent. But if you commit a felony, you'll go to jail. This is called correlation and causation. Correlation does not always mean causation, meaning one does not always cause the other. Here's how it looks in a graph. Let me zoom this in so we can kind of look at it. So I'm going to give you a second. I'm going to talk about this graph. This is margarine consumed. Margarine's butter. Butter consumed and the divorce rate in Maine. So here we go. So we've got these graphs. Look at this. And you can't really tell, so I'm going to highlight for you. The thicker one with the bigger dots, that's this one. This is the butter. I'm going to make the butter yellow. Okay, the butter's on the bottom and then it goes on to the top. All right, the butter is yellow. There we go. Look at that. The margarine consumed correlates with the divorce. Does that mean the divorces cause people to eat less margarine? Or does it mean that butter causes people to not get divorced? Because look, the divorce rate's going down. In 2000, it was way up here. And in 2009, the divorce rate's going down. Well, the less butter eaten is probably not causing people to not get divorced. Maybe you're thinking things like, well, you eat less butter, you're not as fat, and then you know people will like you better or something if you're not. No, that's not how that works. But yeah, the butter's not causing. So correlation does not mean causation. Another one that I like to use is it's really hot at the beach, and the higher the temperature goes, the more drownings there are. Is the temperature causing people to drown? No, but the temperature does drive more people to the beach, and when there's more people, there's a greater chance of someone drowning. So the temperature is not causing the drowning. It's probably because there's more people. So correlation does not always equal causation. So let's take a second look at these. Example 19. So here we go. IB grades achieved by a student are an effect of the predicted grades given by their teacher. Now that one might be a little confusing because you're like, well, I don't understand what that's saying. In IB, you get a predicted grade. I look at the work you do in class, and then I predict what grade I think you're going to get on your exam. Okay? I base it off of the grades you get in my class, questions you ask, how well you do on your test, how well you do thinking on your feet. I look at that. So IB grades achieved by students, so your grades, are an effect of the predicted grades that I give you. IB grades achieved by the student. Not really. My predicted grade has nothing to do with how you do in the class. So I would say, no, not really. My predicted grade, you don't even know my predicted grade. That doesn't affect the way you are as a student. The height of a person is a cause of their weight. Ooh, does height affect your weight? Actually, yeah, it does. And you could kind of go both ways on that. I guess you could say the taller the person, the less they weigh. Maybe somebody's really tall, but they weigh less. But usually your height and your weight do correlate together. But just because you don't weigh very much, does that mean you're tall? Or just because you weigh a lot, does that mean you're short? No. So I'm going to say the height of a person is the cause of their weight. No, not really. It does impact it, but it doesn't cause it. The number of ice cream sold is a cause of high temperatures. Does ice cream cause the temperature? Yeah, no. That one's pretty easy to see. Smoking is a cause of lung cancer. Smoking causes lung cancer. Does lung cancer cause people to smoke? No. But we're going this direction. Does smoking cause... Okay. Now, I would say this is definitely one that we could debate in class. Because we know I'm sure some of us know smokers that never got lung cancer in their life. But does smoking always cause lung cancer? Maybe. Here's where I'm going to say yes on this one, and here's why. Smoking is a cause of lung cancer. Is it a cause? Absolutely. Does it always cause it? No. So if this said smoking is always a cause of lung cancer, absolutely not. Then we'd have no. So here's what we're going to say. In statistics, correlation can be quantified and given a number where 0 is no correlation and 1 is a perfect correlation. Perfect correlations exist, and it is pretty much indistinguishable from causation. We rarely, if ever, use the term causation, and instead you'll be talking about various types of correlations and whether your results are significant. So we're not really going to talk about causation. We're going to focus on correlations and their levels of significance. Significance. Whether they are significant. Okay, singular. Okay, so correlation and causation is important. IB doesn't really focus on that. We're going to focus on how is the data correlated and is it significant? Can we call it significance? Really, this means correlation and causation if there's a level of significance, but we're going to go from there. Now, what we're going to do next, you have already seen in Algebra 1. Already done this. So that is what's really nice about this unit. Linear correlations or bivariate data. That just means it's two decimals. Oh my goodness. Two variables. Bivariate equals two variables. Bi means two. Bivariate data is two. Oh my gosh, I said it again. All right. You're going to have an X, which is going to be your independent. You should know these as well. Y is going to be your dependent. And we're going to have some scatter plots that look like this. Okay, correlations, they look like scatter plots. So I'm going to say correlations look like scatter plots. Here's my scatter plots down here. Okay, if I were to graph this, I would call this, I'm going to get another pen on here. This data goes down. I would call this a negative. It looks like a straight line, so I would call it a negative linear correlation. When I look at this one, I notice it starts low and it and I might even draw this it begins to go up like such. I would call this a positive exponential correlation. I'm going to put I guess I should write it. I should have written it the other spot. Exponential correlation. This one is all over the place. There's no way to figure out where it's going, so I'm going to call this no correlation at all. You're probably already looking at this one and going, oh, that's a quadratic. It's opening down, so we're going to call this one a negative quadratic correlation. And if you want to kind of draw your parabola on it, and this one we might draw an arrow down. All right, so when you're doing this, you have something, and a lot of you are going to do linear correlations in your IAs, which is why I want to take a minute and show you this mean point here. Okay, the mean point. The point associated with the set of bivariate data that has coordinates x, y. So I'm going to focus on linear data for this. So a mean point, let's put a definition here. It's the point associated with a set of bivariate data that, and this is super important, has coordinates. I'm going to write it as an ordered pair. Here it is, x bar, y bar. Remember what the bar means. Bar means the mean. It's the average. So I'm going to average the x values and average the y values, and I'm going to find this ordered pair. It's the mean point. That is called the mean point. The line of best fit, when we're doing linear, will go through the mean point. So let's actually put that. The line of best fit will go through the mean point. Okay, that is super important. In fact, I'm going to actually highlight that. The line will go through, the line of best fit will go through the mean point. And I'm going to actually take my red and point right there, and I'm going to put mean point. Just want to be sure you understand that. Okay, so here we go. So let's take a look at, like, how is this going to look? So Renee wants to determine if there is a relationship between the number of snacks everyone eats each day, X. So I'm going to put, this is the snacks right here, and the time they work out in a week. So I'm going to call this the workout. Workout is the Y. So how many snacks do you eat, and do you work out a lot? So it looks to me like the more snacks you eat, oh, the less you work out. I think I fall here. This is me. Okay, what we want to do is find the mean data point. So remember, the mean data point is the X bar. Well, can you do that? Yeah, that's pretty easy. I'm going to do 2 plus 4 plus 7 plus 9. And what am I going to divide it by? 1, 2, 3, 4. 4 points. Y bar, well, that's going to be add up the y's. So 5 plus 3 plus 6 plus 2. Divide by 4 again. This one right here comes out to be 11 over 2, which is 5.5. And this one comes out to be 16 over 4, which is 4. So here's what I would want to write when I get this answer. And it asked me, this is super important, for the mean data point, I would want to say that X bar, Y bar equals 5.5, comma, 4. Now, just as a reference, if they said write it to 3 sig figs, I could put 5.50, comma, you have some options. Because we just got 4, you could do 4 and call it quits there, and you would be fine. You could do 4.0, or oddly enough, you could do 4.00. Either of those would work, but because 4 is an integer, you could just stop at 4 right there and leave it there. All right, so finding a mean data point is super easy. When you go to do your IA, if you decide you want to use linear regressions, which a lot of you will, and when we go to do Barbie Bungee, you can use that mean data point in your paper. It's super interesting to kind of like look at. All right, so let's talk about Pearson's correlation coefficient. You've already done this. You already know this. I hope you remember it because we did it a lot in Algebra 1. We had a lot of fun with it. So this is called, I know it's a mouthful to say, Pearson's product moment correlation coefficient. It is the R. You have it on your calculator. So I'm going to say equals R. It's the lowercase r. Now, we are going to shorten this to Pearson's product moment correlation coefficient. Yeah. PPMCC, we're not. We're going to call it Pearson's is what I'm going to call it. All right, so I've got this chart over here. R has a value when you get it. The closer you are to the number 1, and think about it like this. You've got all these little scatter plots. When these dots move together and they make a straight line, it's like the number 1. That is a strong correlation. But when the dots are real spread out and they're kind of all over the place, that's a very weak correlation. So from 0.7 to 1, it is a very strong correlation. I'm going to show you what that looks like. I did, let's see, 1, 2, 3, 4, 5. I don't know what this one was. I'll come back to that one. I was looking on my notes to see what I did. I think I was doing a, let's just say this. Let's call this, if my line looks like this, this is what I call a perfect correlation. That is a perfect correlation. And on this, the R value would equal 1. This scenario right here, I would call a positive correlation because it's going up. It could go the other way and it could go down, and I would call that a negative. But I'm going to hold off on doing that. I'll do it in a second. So here's what I've got. I'm going to say that when you go from, which way do I want to go? I want to go, I'm going to call this a strong positive correlation. So this is going to go from 0.7 less than or equal to R less than or equal to 1. So this is when you're at 0.7 all the way up to 1. I'm going to do these in red. It's a positive correlation because R is positive, and it might look something like this. You're going to be able to tell that it's going up in a positive fashion, and you notice that your dots are pretty close together, right? The dots are pretty close together. All right, so that was this one right here, strong positive. Now, what happens if we have a weak to moderate positive correlation? So we're going to call this a weak positive correlation. This is going to go from 0.3 less than or equal to R less than or equal to 0.7. All right. So again, it's still positive, so I can still see that it's going up like this, but maybe the data is more spread out. And so you can still see that it's going up, and maybe these outliers out here kind of throw it off a little bit. It's still going up. We can still see that. But the data is more spread out. And so if I were to draw the line through it, it might look something like that. I didn't do that earlier. One thing to note, I should have done that on here. You see how I'm always starting here at 0 down here at the bottom? You don't have to. Your line could be up here. We'll do that on the next one. Okay, so now we've done what a strong positive, what a weak positive. Let's do no correlation. So no correlation. No correlation. So this is from negative 0.3 less than or equal to R less than or equal to 0.3. On this, my data is just, you can't figure out where to put anything. It's too spread out. You just can't tell what's going on. Maybe this right here, but no, well, maybe this right here. You can't tell. So there's what we call no correlation. Then we move back out to a weak negative. So this one is negative, excuse me, negative 0.7 less than equal to r less than or equal to negative 0. You know what? I was looking at this. I just now noticed I did put equals to on these, and it's saying you don't have to. I'm going to say you can put it there because it could go either way. All right, so this is going to be our negative, weak negative. So that means your data is coming down like such, but it's kind of spread out, right? So you can't quite tell. You see that it's trending down, but you notice that, you know, it's a little more spread out. So it might look something like that. Weak negative. And then the last one, as we move out, we're going to go into our strong negative correlation. And on this one, it's going to be a strong negative. So that means it's negative, but it's definitely the data is closer together. And it looks like this. So this is negative 1 less than or equal to r less than or equal to negative 0.7. And again, if it's a perfect correlation, it's going to be perfectly positive or perfectly negative is what I tend to always say. All right, so I think we got our strong positive, our weak positive, our no correlation, our weak negative, and our strong negative. And up there we've got our perfect one. All right, again, these all deal with linear. Pearson's product moment is for linear correlations. So here's what I've got. How to calculate Pearson's R value by hand. When you do your Barbie bungee, we are going to calculate Pearson's product moment by hand. Take a second and look at that. You know the terminology. The sum means we're going to sum up x times y minus n x bar y bar, meaning the average, and then we're going to take the square root of all of this and multiply it by the square root of all of this. Okay? So we're going to do it by hand, but we're going to do it with the help of our calculator as well. So here we go. I'm going to call this L1, and I'm going to call this L2. First thing I want to do is find x bar, and I want to find y bar. We're going to do this by hand, and then we'll use our calculator. We know how to do x bar. It would be 5 plus 7 plus 12 plus 16 plus 20 divided by 1, 2, 3, 4, 5. And then y bar would be 4 plus 12 plus 18 plus 21 plus 24 divided by 5. Now I am going to jump over to my calculator. I'm going to do it on my calculator even though I just set it up. You know, I set it up with my, clear that out. I set it up with my, what do I want to say, my hand. I like doing it by long ways, but I'm going to do the math here. So 5, comma 7, comma 12, 16, 20, and then 4, 12, 18, 21, 24. Okay, so L1 and L2, I put both of my data in. You may remember this whenever we did it before. Okay, so I'm going to put that aside for right now. Double checking. Yeah, that's what I wanted to do. Yeah. So I wanted to double check real quick. We're going to calculate. Normally, you're used to going here linear regression. We're not there yet. We're still just wanting to know the statistics part of this. What's the central tendencies? I'm going to go to 2 variable because that's what I have. List 1 and list 2. And there we go. Do you see X bar and Y bar? It's already there for me. 12 and 15.8. If I were to do these, I would get 12 and 15.8. So this is 12 and this is 15.8. Okay, so I know my X bar, and when I worked it was like 60 divided by 5 and 79 divided by 5, I think is what we did. All right, so let's do, I'm trying to think how I want to set this up. I need to have X times Y, right? X times Y. I need to have N times X times Y. N's the number of our terms. We have 1, 2, 3, 4, 5. So let's go here. Let's put N equals 5. And then let's put 5 terms or 5 data. Maybe we should call it data points. Okay. We could say that X bar equals, if you sum all of these up, it's 60 divided by 5. And Y bar equals, if you sum all of that up, it comes out to 79 divided by 5. So I want to think, I'm trying to think when you guys, I don't have notes on this yet, so we're kind of doing, I just thought we'll do it here together. Let's set up a table. No, you know what? Let's just do this. Let's do the sum. We're going to do these sums up here of all the x squareds, okay? All the x squareds. And then let's do the sum of all the y squareds. And then I should have left myself a little hand. You need to do this by hand on your IA, the sum of all the x times y's. Okay, so let's sum up all the x squareds. Now I want to write it out, okay? The sum of all the x squared is going to be 5 squared plus 7 squared plus 12 squared plus 16 squared plus 20 squared. I hear my family coming in, so it might get noisy here in a second. Now, for the essence of the video, I'm not going to put all that in because it would take me a while, but I know you know how to do this. I got 874. To sum up the y squareds, on your IA, can you do it like this? Yeah, you could. You could also maybe create an Excel spreadsheet and set it up that way where you put the data in and then you list it out like this. Okay, so I'm going to square all the y's. And that equals, again, I'm not going to use my calculator because it takes too long. Why did I pick these numbers? I'm looking up here at what I need. I need x times y. I need x bar times y bar. Well, those are easy to do. I need x squared, x squared, x squared. I've already got that. Y squared, I got that. Y squared, ooh, to the negative 2. Actually, I don't think that was, I want to look. I can't remember. Oh, yeah. It looks, I remember when I did this, it looks like a negative 2. That bar is over the y. It's not negative 2. I'm glad I remembered to tell you guys that. Okay, and then x times y. So we'll do 5 times 4. I'm going to do parentheses. Plus 7 times 12 plus 12 times 18. I put that both in parentheses. Plus 16 times 21 plus 20 times 24. And again, for the time of the video, I'm going to save you guys from doing that. We're going to get 1,136. Okay. All right. So I'm going to calculate R now. I'm running out of room, but I'm going to try and do this. So here we go. I am going to put this where I'm going to try and fit it right there. Actually, no, I'm going to come down here. I feel like I'm not going to make it if I do it. Okay, so R equals. Here we go. This is the part that you're going to be careful with on your IA. I'm going to pull back a little bit so you can see the formula I'm following here times this. Okay, remember, I didn't say this before, but this means the sum, which is why I added all that. The sum of all the y squared. Okay, so here we go. The sum of the x times the y's. The sum of the x times the y was 1136. There's that one. Minus. Now we need to do 5 times x bar, y bar. 5, because 5 was the data. X bar was 12. Y bar was 15.8. Divided by, we're going to be careful here, the square root, the sum of the x squareds, which was 874, minus 5 times x bar squared. X bar was 12, and I'm only squaring the 12. I'm going to extend that over a little bit. And then it's multiplied by, so I'm going to go ahead and put parentheses around this. Parentheses, and then another square root. The sum of the y squareds. Y squared is 1501 minus 5 times the y squared, which is 1501. Ooh, pull that out. Oh, I'm sorry, that's not, I didn't do that right. The y bar, not y squared. Glad I caught that before we got, okay. N times y bar. Y bar is 15.8. And then I want to square that. I'm going to double check. 1501 minus 5 times 15.8. 5 squared. I'm just double checking my math. Okay. So here is how you calculate R. Now, put that in your calculator. You are so going to want to use alpha y equals. It will make your life easier. And then on the top, we're going to put 11. You know what? I don't even have to do that. Let me do this. 1136 minus 5, parenthesis 12, parenthesis, 15.8. That's what my top would look like. On the bottom, just a little bit. On the bottom, I'm going to have parentheses, second square root. And then I'm going to do 874 minus 5, parenthesis, 12 squared. Move out from underneath the radical. Close your parenthesis and then put another parenthesis. And then second square root, 1501 minus 5 times 15.8 squared. And then move out. And then double check that you close everything. So I've got these big parentheses times these. And I want to make sure that 1501 dash 5, 15.8 squared. Okay, you might notice that these look different, but it doesn't matter. It's still just squaring the 12. All right, if I did it right, I got R is 0.9528. Oh, I get it right. Boy, you get nervous when you're doing those numbers. Like, you'll feel much better when you're doing it on your calculator because when you're using the regression, because you just feel safer. Okay, so 0.9528 ... just meaning it goes on and on. But I need to do 3 sig figs. So I'm going to say it's approximately 0.95. The 8 rounds the 2 to a 3. So R equals 0.953. Now, just looking at the R value, which category does that fall in? Where does 0.9 fall? Positive 0.9. It falls right between here, right? That means this is a very strong correlation. Going back to what I said, the closer you are to the number 1, the stronger the correlation. When I taught it to you in Algebra 1, I said the closer you are to $1, the stronger the correlation. 95 cents, ooh, that's almost $1. And so that's how that worked. All right, last thing I'm going to show you on here is just your calculator tips. We're going to go here. You've put this data in, right? So we are going to, oh, I should show it to you on here. We're going to follow these steps. So you've got your data in. We're going to go down to calculate, and we're going to go down to a linear regression. Okay, that's where we're going, number 4. You're going to hit enter. You're going to make sure L1 and L2 is the frequency list, but we're going to store, down here on the store, we need to put Y1. How do you get that? You go, I don't think there's another shortcut. I'm just going to double check. I've never seen another shortcut. Yeah, alpha Y equals y var. It means y variable. Which y variable do you want? We want the first one. That is just where it's going to store it. On my y equals button, it's going to do it in y1. I'm going to tell it to calculate. All right, so I did that. And I see this, right? Now, here's what I'm going to do. I don't see the R value, so I have to turn the R value on. So you're going to hit Mode, and see where it says Stat Diagnostic, turn it to On. So go down to Stat Diagnostic, go to the On, hit Enter, and it puts it over there. Now we're going to do the same thing over here. We're going to hit Stat, calculate number 4 again, enter all the way through. Oh, I forgot to store it. Stat, calculate number 4. I'm going to store it. Alpha y equals, the variable I want is the first one. And I can see the R. Oh, wow, it's the same R. Okay, so what I want to do is I want to plot this data on my calculator. So I go to Second, Stat Plot. I'm going to make sure I turn it on. So I'm going to hit, it's on, right? I'm going to hit on. Now, I don't want to be in a box and whisker plot. What I want to do is I want to plot the data, the dots. I'm going to hit Enter. And I'm going to go to y equals, and there's that weird equation that I just found. I'm going to hit Graph, and there it is. But I can't see anything, so I'm going to hit, I should have put that on there. Zoom number 9, I believe it is. I'm going to write that on here. Zoom number 9 to see data points. Now, you might be thinking, what? That's different. Yeah, that's not the one that I was doing. That is just a sample. All right, and you can see it. There's my points. And so you can see, yeah, those points are almost in a straight line. That is a strong positive correlation. All right, so we are going to do some examples, but I am going to stop the video, I think. Oh, maybe I can get it in. Here's what I'm going to do. I'm going to do this because my family's about to be here. We're moving a house. My daughter's moving in. So I'm going to put this right here, and I'm going to zoom this out. Actually, I'm going to zoom it in. Calculate by hand. This is what you should get. I'm just going to put these here for you guys to see. Let me zoom that out a little bit. Move that up. Move that up. All right. So pause your video. See if you get what I got. Thanks for watching, y'all.